Good afternoon, everyone. My name is Shaharuddin. I'm with the National University of Ireland, Galway, and my topic for presentation today is on novel scintillation detectors for ultra-high dose rate X-ray beam. So I'll begin my presentation with the introduction to flash radiotherapy, the new medical physics application that we're looking into. Then I'll introduce the novel inorganic scintillation detectors. I'll show you some of the previous works that we've done with the ISD, the inorganic scintillation detector, and I'll talk about the experimental method specifically for this application, and then I'll discuss the results and conclusion. So for the past decade, we've seen an increase in medical ionizing radiation application. We have IMRT, intensity modulated radiation therapy. We have proton radiotherapy, and the latest one being flash radiotherapy. So flash is a new technique that delivers a single pulse of ultra-high dose rate beam at typically more than 40 gray per second. And for comparison, a conventional radiotherapy delivers fractionated low doses at a low dose rate, so typically less than 0.03 gray per second. So ultra-high dose rate beam has reproducible results that shows it significantly reduces radiation-induced tissue toxicity in normal tissue, but it still maintains the tumor control activity. So therefore, it widens the therapeutic window in radiation therapy. And so this technique has a capability to modernize radiotherapy treatment, but the challenge in implementing it clinically is to have a reliable real-time dosimetry system. And so just to put into context, standard dosimeters that are used in conventional radiotherapy suffers from high saturation effect or reduce ion collection efficiency when it's subjected to high energy radiation field. And those that can measure high dose per pulse usually cannot provide real-time measurements. So a novel detector for medical physics applications are scintillators. Scintillators in general emit light when it is subjected to ionizing radiation and couple it to an optical fiber. The light travels through the fiber to a photon counter or an optical reader, and then that generates electrical signals that are proportionate to the ionizing radiation. So in medical radiation dosimetry, the material used typically are plastic or organic based, and that is because the plastic scintillators are have water equivalent properties. Inorganic scintillators does not, but inorganic scintillator powders, inorganic scintillator materials have much higher light output compared to plastic. And so here we propose the use of inorganic scintillator powder coupled to an optical fiber for the dosimetry of ultra-high dose rate X-ray beam. That comes to the aim of our project. We want to investigate whether the ISDs are capable of measuring ultra-high dose rate X-ray beam or not. So some of the advantages, as I mentioned before, that ISDs have much higher X-ray absorption coefficient compared to a plastic organic scintillators. So it gives us a higher light output, and ISDs are also dose and dose rate linear, meaning it's independent of those two parameters. However, we note some of the challenges in using these materials for this specific application is the stem effect or Cherenkov radiation that occurs in the optical fiber when you give a high energy radiation. ISD is also a high-Z material, meaning that it requires correction factors because it is not water equivalent, and this can be a problem in medical radiation. So some of the previous works that we've done with the ISDs, firstly, the work was done by Al-Harbi et al. In 2019 for an external beam radiotherapy that uses 6 MV photon beam. And here the detector was 700 micrometer diameter and 7 millimeter length. The detector showed an excellent repeatability and reproducibility, and it was also independent of the dose rate given. However, the detector exhibited dose per pulse dependence and also angular dependence. The next one, the next optimization work was done by Burnett et al. For small beam field application called the Small Animal Irradiation Research Platform. And so the scintillator material here was optimized to 3 millimeter, but the diameter was still maintained at 700 micrometer. the detector showed a very large signal output compared to PSD because Bernadette also compared the detector to a plastic scintillator. And the beam profile agrees with the plastic scintillators one. Here again, the detector exhibited excellent repeatability and reproducibility, and it was also independent of the dose rate given. So that comes to the design of our ISD for this specific application. We still maintained the materials and the design, the overall design, I mean. We used a PMMA optical fiber that was micro-machined to create a bore. Here we reduced the scintillator's length from 7 millimeter to 1 and 2 millimeter. We also reduced the diameter of the scintillator to 500 micrometer to account for the possibility of high saturation effect. And then after filling the bore with the scintillating powder, we seal it with epoxy. So these are the three materials that we use for the ISD fabrication. We use terbium-doped gadolinium oxysulfide, terbium-doped lanthanum oxysulfide, and europium-doped lanthanum oxysulfide. So because all of these materials are in powder form, the challenge was in packing the material into the optical fiber, but the micro CT scan show here on the image below, it shows a uniform packing for all detectors. So that was good. And the next step was to irradiate the detectors. Here we use a conventional X-ray tube that was modified with a shutter system to deliver an ultra-high dose rate beam. And so the detector was connected to an optical reader by Hyperscint, and the signal was processed using the proprietary software. And back to the X-ray tube here, the shutter system controls the amount of radiation delivered. So in other words, it controls the dose delivered to the detector, and the tube current from the system controls the dose rate of the radiation given. And so here we investigate the detector's linearity as a function of the tube current, one. And secondly, we investigate the detector's linearity with the tube shutter's exposure time. Lastly, we subject the detector for multicolor simulation, mainly because we wanted to calculate the dose absorbed to water for the scintillator detectors, and we use the topaz code here. So for results, all of the scintillator profiles were normalized 100% to 80 kVp X-ray beam at 25 milliamp for a 100 milliseconds shutter exposure time. Overall, all scintillator profiles exhibited a symmetrical beam profile and good signal-to-noise ratio. So as I mentioned, we investigated the detector's linearity with the shutter exposure time, that is the amount of dose delivered, and our linear regression analysis here showed 0.999 for all detectors, meaning they are all independent of the dose delivered. And also here we can see that the detectors was also linear with the tube current, meaning it's independent of the dose rate given. The linear regression analysis here also shows 0.999 for all detectors. So that is it for the study at this moment. For conclusion, we have fabricated ISDs using optical fiber and phosphor-based scintillating powder for ultra-high dose rate beam. The results show good scintillator output profile, good signal-to-noise ratio, and excellent dose rate linearity for tube current up to 25 milliamp. It also showed excellent dose linearity up to 100 millisecond radiation exposure. And so we are still conducting an ongoing research to determine whether ISDs are a good alternative for ultra-high dose rate beam or flash radiotherapy. And so for this, we need the correction factors for each of the material of the scintillator. And we also require another Monte Carlo simulation for the calculation of the maximum dose rate absorbed to the ISDs. And also we need to benchmark the performance of the ISDs to already characterized plastic scintillators done by Cecchi et al. In 2021. So here I would like to acknowledge everyone that's been involved in this project, especially from Medicine, Galway Clinic, and the Engineering College and NUI Galway. So this is my reference. Thank you for listening today. Bye.